There is something almost unbearable about the idea of sending something away, and knowing you will never get it back. Not lost, not destroyed, just gone, moving outward, forever, past every planet, past the last gasp of the solar wind, past the invisible line where our sun's influence quietly surrenders to the ancient darkness of interstellar space. In 1977, humanity did exactly that. Twice. We launched 2 probes into the void with the full knowledge that they would never return. We gave them names, filled them with instruments, and loaded them with a golden record containing the sounds of our world. Whales, thunder, laughter, music, greetings in 55 languages, as if we were slipping a note under the door of the universe, hoping someone on the other side might one day find it. And then we watched them go. Nearly 50 years later, those 2 machines are still out there, still transmitting, still, in some improbable and deeply moving way, alive. Voyager 1 is now more than 25 billion kilometers from Earth. Voyager 2 is not far behind. They are the most distant human-made objects that have ever existed, and they continue to tell us things we did not know before. What they have shown us about Jupiter, Saturn, Uranus, Neptune, and the strange, turbulent boundary between our solar system and everything beyond it, rewrote entire chapters of planetary science. What they continue to show us, even now, keeps rewriting the chapter we thought was already finished. This is the story of the Voyager missions, from the spark of an idea that almost never happened, to the engineering that defied every reasonable expectation, to the impossible discoveries that transformed our picture of the solar system, to the slow, quiet fade of 2 machines that were only ever supposed to last 5 years, and to the question that sits at the heart of all of it. What does it mean that the furthest thing humanity has ever made is still moving away from us right now as you watch this? Let's find out. Every great story has a door that was only open for a moment. In the mid-1960s, a graduate student at Caltech named Gary Flandreau was working on a routine NASA study when he stumbled onto something extraordinary. He noticed that, in the late 1970s, the 4 outer planets of our solar system, Jupiter, Saturn, Uranus, and Neptune, would briefly arrange themselves in a configuration that occurs only once every 176 years. In this alignment, a single spacecraft could theoretically visit all 4 giants in sequence, using each planet's gravity like a slingshot to fling itself toward the next destination without burning additional fuel. The concept had a name, the Grand Tour. The problem was the timing. The window would open in 1977 and close within a few years. If NASA didn't launch by then, no one alive on Earth would ever have another opportunity. NASA had a decision to make. Congress wasn't prepared to fund the full Grand Tour. Too expensive, too risky, too ambitious. What they agreed to fund instead was a more modest mission. 2 probes, a 5-year lifespan, designed to study Jupiter and Saturn. If they survived after that, well, perhaps they could be redirected. So NASA's engineers made a choice that would prove one of the most consequential in the history of space exploration. They built the probes as though they were going to last far longer than anyone was willing to officially admit. Redundant systems, long-duration power sources, backup computers, heaters, extra thrusters sitting idle, waiting for a moment of need that might never come, or might come 4 decades later. It was an act of quiet, stubborn optimism dressed up as engineering. Voyager 2 launched first, on August 20th, 1977, from Cape Canaveral. Voyager 1 followed 2 weeks later, on September 5th. Despite leaving second, Voyager 1 was placed on a faster, shorter trajectory, overtaking its sibling by December of that year. They were aimed at a rare planetary alignment, carrying 5-year technology, built by people who dared to imagine 50. What happened next justified every one of those dares. Before we follow the Voyagers on their journey, it is worth pausing to understand what kind of machines these actually are, because the gap between what the Voyagers were designed to do and what they have actually accomplished is one of the most quietly astonishing engineering stories in history. Each probe is powered by a radioisotope thermoelectric generator. essentially a device that converts the heat produced by decaying plutonium-238 into electricity. At launch, each generator produced roughly 157 watts. That is about enough to run 2 incandescent light bulbs. It might sound modest, but it was more than the probes needed. And crucially, plutonium-238 has a half-life of nearly 88 years, meaning the power output diminishes slowly enough that both probes were able to keep essential systems running for decades longer than planned. For navigation and orientation, each probe carries gyroscopes, pointing instruments, and 16 thruster jets, 8 primary, 8 backup. Those backups proved their worth when, after 37 years of complete inactivity, Voyager 2's backup thrusters were switched on following the failure of the primary set. They ignited. They worked perfectly. After nearly 4 decades sitting idle in the frozen dark between planets, they fired as though they had never stopped. The onboard computers are, by any modern measure, astonishingly primitive. They have less processing power than a digital wristwatch. They store data on 8-track magnetic tape technology developed in the early 1970s, a format older than most of the people who have worked on the mission over the decades. Each probe carries a 3.7-meter dish antenna for communicating with Earth and a digital tape recorder capable of holding enough data for roughly 100 photographs. Yet this ancient, limited hardware has survived asteroid belts, intense radiation, temperature swings of more than 100 degrees Celsius, and 5 decades in deep space. In 2022, when a technician on the Voyager team discovered that the probe was transmitting garbled navigation data, the solution ultimately came down to the fact that, in the intense radiation environment of interstellar space, the spacecraft had begun routing data through an older, faulty backup computer instead of the correct one. The fix was essentially to tell it to stop doing that, and it listened. These are not sophisticated machines by the standards of what we build today. They are something rarer than that. They are durable ones. Voyager 1 arrived at Jupiter on March 5th, 1979, having covered 714 million kilometers in a little under 18 months. What it found there shattered assumptions that had been sitting comfortably in textbooks for decades. Scientists knew Jupiter had an atmosphere, of course. They expected it to be banded and zonal, orderly lines of wind moving in one direction in one band, the opposite direction in the next. What Voyager found instead was chaos. Not metaphorical chaos, literal, visual, jaw-dropping atmospheric violence. Vast hurricanes the size of continents, plumes of cloud material twisting upward and outward, complex eddies and rotational formations in every region of the planet's cloud layer that nobody had predicted. The Great Red Spot, which scientists had long suspected was a rotating storm system, was confirmed, and it was more dramatic up close than anyone had dared imagine. A counterclockwise hurricane larger than the entire Earth, surrounded by smaller storms that had never been observed before. Jupiter's atmosphere, it turned out, was not a banded ribbon running quietly around the planet. It was a world of perpetual, unrelenting meteorological war. Voyager also confirmed what pioneer data had hinted at. Jupiter has rings. They are nothing like Saturn's, faint, dark, made of fine dust particles. But they are there, and we would never have known without these images. Voyager 1 didn't just look at Jupiter's surface. It measured it, mapped it, watched it move. During the approach phase alone, scientists compiled 66 photographs taken at 10-hour intervals, one complete Jovian day, and assembled them into a time-lapse sequence that showed the planet rotating beneath the probe as it closed in. For anyone who has ever seen that footage, it is one of those images that stays with you. This enormous alien screaming world, churning in silence from 67 million kilometers away. And this was only the first stop. If Jupiter's atmosphere was a surprise, its moons were something close to a revelation. Before Voyager, scientists expected Io, the innermost of Jupiter's large moons, to look something like our own moon, ancient, pockmarked, a frozen record of a violent past, long since cooled into quiet. What the probe actually found when it turned its cameras toward Io's surface stopped mission scientists in their tracks. There were no craters. Where craters should have been, there were dark oval patches, not impact scars, but volcanic calderas. There were lava flows that looked geologically recent. And then, almost impossibly, there were actual eruptions happening in real time. Plumes of gas and material shooting 100 kilometers into the vacuum above Io's surface, caught on camera as the probe flew past. Several eruptions were imaged over the course of the flyby. Scientists watching the images come in were looking at a world that hadn't simply been geologically active once. It was the most volcanically violent place in the entire solar system, going off relentlessly, continuously, driven by the tidal forces that Jupiter and its other large moons exert on Io's interior. It was the last thing anyone expected to find. Then Voyager turned its cameras to Europa. Europa could not have been more different. Where Io was screaming fire, Europa was silent and pale. Its surface was a near-perfect shell of ice, almost devoid of the impact craters that covered most airless worlds. And crossing that ice, in every direction, were long, shallow markings, fracture lines, running across the surface like cracks in the shell of a hard-boiled egg. What was breaking those cracks open? The data Voyager collected raised a possibility that has driven Europa science ever since. Those fractures might be forming because the ice is floating, not resting on bedrock, but drifting on the surface of a liquid ocean, an ocean kept from freezing by the same tidal forces that make Io volcanic, pressing and releasing the moon's interior like a hand slowly squeezing a wet sponge. Voyager couldn't confirm it, but it put the question on the table, and that question has never left. 21 months after Jupiter, Voyager 1 arrived at Saturn. Voyager 2 followed 9 months later. If Jupiter had been defined by chaos, Saturn was defined by beauty, and then by the disturbing discovery that the beauty was not at all what it appeared to be. The rings of Saturn were already known, of course. Astronomers had been observing them through telescopes for centuries. Before Voyager, the working model was that Saturn had 5 major rings, broadly separated, each one a relatively uniform structure of ice and rock. What Voyager found was something almost impossibly complex. Those 5 major rings were not 5 rings at all. They were hundreds of them, hundreds of thin, concentric ringlets, packed together, each with its own properties, its own density, its own slight variation in composition. The resolution of Voyager's images revealed structure within structure within structure, like a piece of music you thought you understood until you heard it at full volume, and realized it contained instruments you had never noticed. There was a ring nobody knew about, the G ring, faint and thin, identified for the first time. There were what scientists called spokes, dark, radial features drifting across the B ring like shadows of clouds on a field, moving in a way that orbital mechanics simply couldn't explain. Gravity should have spread them out and broken them apart almost immediately. Instead, they persisted. The leading explanation involves electrostatic forces lifting tiny dust particles above the ring plane, but the mechanism still isn't fully understood. And then there was the more sobering discovery. Saturn is losing its rings. Gravity is slowly pulling the ring material down into the planet's atmosphere, raining ice particles inward at a rate significant enough that, given enough time, the rings will be gone. According to NASA's models, Saturn may be ringless within 300 million years. On a cosmic timescale, we are lucky to be alive at a moment when the most visually iconic planet in the solar system still has its defining feature. Voyager gave us that ring system in full, breathtaking detail, and then told us quietly that we are watching it disappear. Saturn's rings were extraordinary. Its moons were something else entirely. Voyager had already added 3 new moons to Jupiter's count. At Saturn, it found 3 more, bringing the known total at the time to 17. But it was what the probe discovered about 2 moons in particular that left the deepest marks on planetary science. Titan was the first priority. Saturn's largest moon had been of interest since Pioneer 11 passed through the Saturnian system a year before Voyager's arrival. The data suggested Titan had an atmosphere. Voyager confirmed it, and then went considerably further. Titan possessed a thick, nitrogen-rich atmosphere, the only one of its kind found on any moon in the solar system. The nitrogen content alone was striking. Here was a world with an atmospheric chemistry that, in certain key respects, resembled the early Earth. Scientists studying Titan's atmosphere saw precursor molecules for the kind of organic chemistry that, under different conditions, might lead somewhere very interesting indeed. The probe couldn't see through the haze to Titan's surface. That would have to wait for another mission. But the atmosphere itself was enough to make Titan one of the most compelling objects in the solar system, a status it retains today. Then there was Enceladus. Enceladus looked, at first glance, like a geologically quiet moon. And then Voyager looked at it more carefully. The surface showed something unusual. Two distinct and incompatible terrains side by side. On one side, ancient, heavily cratered ground. On the other, smooth, young surface, with almost no craters at all, as though the older material had been resurfaced, erased, replaced by something welling up from below. Voyager data pointed toward internal geological activity, which shouldn't have been there, which nobody had predicted. Decades later, when the Cassini spacecraft flew close enough to look properly, it found what Voyager had hinted at. Enceladus was erupting plumes of water vapor from cracks near its south pole, shooting material hundreds of kilometers into space and feeding one of Saturn's outer rings directly. Below its icy crust was a liquid water ocean. Voyager had looked at Enceladus in 1981 and seen something was strange. It took another spacecraft and another 20 years to understand what it had actually found. After Saturn, Voyager 1's trajectory bent upward out of the plane of the solar system, and its planetary work was done. Voyager 2 continued alone. It would be the only spacecraft to ever visit Uranus and Neptune. Those visits remain the only close looks humanity has ever taken at either world. Uranus was first, in January 1986. The probe passed within 81,500 kilometers of the cloud tops and revealed a planet that was, in several important ways, profoundly weird. Its axis of rotation is tilted at 98 degrees, effectively on its side, rolling through its orbit like a ball rather than spinning like a top. Its atmosphere appeared at first almost featureless, a smooth blue-green haze that seemed almost serene compared to the turbulent giants Voyager had already visited. But beneath that apparent calm was something genuinely puzzling. Voyager data revealed that Uranus has a magnetic field, which was already uncertain. But more than that, the field is tilted at 59 degrees relative to the planet's rotational axis. On Earth, the magnetic and rotational poles are only about 12 degrees apart. On Uranus, they exist in entirely different places, meaning the magnetosphere wobbles and tumbles as the planet rotates, producing a magnetic environment so irregular that scientists still struggle to fully model it. Voyager also found 10 new moons and 2 additional rings, bringing known totals significantly higher and revealing a ring system made almost entirely of fine dark dust. Then came Neptune. Voyager 2 arrived at Neptune on August 25, 1989, 12 years after launch. It passed just 5,000 kilometers above the North Pole, the closest flyby of any planetary encounter in the entire mission. Neptune greeted the probe with winds measuring nearly 2,400 kilometers per hour, the fastest ever recorded anywhere in the solar system. A massive storm churning counterclockwise in the planet's southern hemisphere, the Great Dark Spot, dominated its deep blue face. Neptune was not quiet. Neptune was violent, dynamic, and as full of surprises as every planet before it. Voyager discovered 6 new moons at Neptune and imaged the planet's rings for the first time, finding that several of them were not complete rings at all, but arcs, partial structures of clumped material that shouldn't have been stable, shouldn't have maintained their shape, but did. As Voyager 2 swung around Neptune and its largest moon Triton, a frozen, geyser-scarred world in a backward orbit that shouldn't be there either, and pointed itself toward the long dark ahead, it had finished the only grand tour of the outer solar system ever attempted by a human spacecraft. It may be the only one ever. In February 1990, with Voyager 1 now 6 billion kilometers from home, NASA made a decision it very nearly didn't make. The cameras were going to be turned off. They were no longer scientifically necessary, and keeping them running drew power that would be needed for the instruments monitoring interstellar space. It was the practical choice. But Carl Sagan asked for one more image. He had been advocating for it for years. The idea of turning the camera around and taking a portrait of home from the farthest vantage point any human object had ever occupied. NASA agreed. On February 14, 1990, Voyager 1 rotated, aimed its camera back toward the inner solar system, and took a photograph. In the resulting image, Earth is a single pale blue pixel, barely visible against the scattered light of the sun, fractionally bright inside a thin brown band of refracted color. It occupies less than 1/10 of a pixel. Everything that has ever happened in human history, every civilization, every war, every piece of music, every act of love or cruelty or courage, took place on that fragment of light. Sagan wrote about it with a clarity that has never faded. This image, he said, underscores our responsibility to deal more kindly with each other and to preserve and cherish the only home we've ever known. And then the cameras were switched off, permanently. The dot is still there. We are still on it. The probe is still moving away. The photograph is not just a scientific record, it is a mirror, held up at 6 billion kilometers distance, showing us something about ourselves that is difficult to look at directly and impossible to forget once you have. After the cameras went dark, the real unknown began. To reach interstellar space, both Voyagers had to cross several distinct thresholds that scientists understood mostly in theory and had never once been able to observe directly. The first was the termination shock, the point where the solar wind, streaming outward from the sun at supersonic speeds for billions of kilometers, finally slows down as it meets the resistance of the interstellar medium. Voyager 1 crossed this boundary in 2004. Beyond it lay the Helios sheath, a turbulent, thickening region where the slowing solar wind piles up, growing denser and hotter before it reaches the final boundary, the heliopause. The heliopause is where the sun's influence ends. It is the membrane between our solar bubble and everything outside it. On July 25, 2012, Voyager 1 crossed it. The probe detected the sharp increase in plasma density and the spike in galactic cosmic rays that models had predicted. It became, officially, the first human-made object to enter interstellar space. But something strange didn't happen. The ambient magnetic field didn't change. Every theoretical model had predicted it would. Beyond the heliopause, the magnetic field should have shifted orientation, reflecting the influence of nearby stars rather than the sun. It didn't. NASA held back its announcement for nearly a year, wrestling with the data, trying to understand what they were seeing. Voyager 2 crossed the same boundary in 2018, at almost exactly the same distance, even though models suggested the boundary should have been expanding at that point in the solar cycle. It also detected no magnetic change. What these crossings have revealed is that the boundary between the heliosphere and interstellar space is far more complicated and irregular than anyone had modeled. It is not a clean membrane. It is a turbulent, magnetically unstable zone, possibly shaped by the ancient explosion of supernovae that formed our corner of the galaxy billions of years ago. The Voyagers found magnetic bubbles in the Helios sheath. They found asymmetry in the heliopause. They found an interstellar medium that behaves differently than the equations said it should. Every answer has come packaged with 2 more questions. And now, even the machines are fading. Voyager 1 has experienced multiple computer anomalies in recent years, each one requiring weeks of careful, long-distance diagnosis. Communication takes over 23 hours in each direction. Sending a message and waiting for a reply takes nearly 2 days. Engineers work with the patience of archaeologists, testing ideas gently, knowing that one wrong command sent across 25 billion kilometers of void could silence the mission forever. Eventually, it will go quiet. Both of them will. The power will drop below the threshold needed to run even the most basic instruments, and the last transmission will arrive here on Earth, and no more will follow. But the probes will keep moving. In 40,000 years, Voyager 1 will pass through the neighborhood of a star in the constellation Camelopardalis. Voyager 2 will drift to within 1.7 light-years of Ross 248. In 296,000 years, it will pass close to Sirius, the brightest star in our night sky. Both probes carry their golden records still intact, those strange, beautiful capsules of humanity. Our music, our voices, our photographs, our greetings in 55 languages. They will almost certainly outlast our sun. They may drift through this galaxy for billions of years after Earth is gone. Think about what that means. In 1977, 2 engineers sat down and decided to build something that would work in conditions they couldn't test, survive timescales they couldn't plan for, and cross distances that their instruments couldn't yet measure. They built redundancy into everything. They chose power sources that would decay slowly. They wrote code for computers they knew would eventually be older than anything still in use. They aimed 2 machines at a narrow window in the sky and sent them through it. And right now, at this exact moment as you're watching this, both of those machines are still out there. Still sending. Still, in the oldest and best sense of the word, exploring. If there is a more human story than that, I haven't heard it. I'll see you in the next one.